continue on and let's resume with our final exam review. This is part 2 of the final exam review. So we last left off, we calculated the moles of our acid H3A. And to calculate the concentration, so concentration is just moles over liters. So we take our 0.003 moles of H3A and we divide by the volume of acid titrated, which in this case is 35 milliliters. So we're dividing by 35 milliliters, and we know that in 1 milliliter, we have 10 to the negative third liter. So if we punch that into our calculator, we have 0.003 over 35 times times 1,000. And that in turn gives us 0.086 molar, which we in turn round to 0.09 molar. Does this example make sense? Does this look very similar to the acid-base titration questions that we've handled previously? Any questions on this example? If not, let's continue on. So for Lewis structures and molecular geometry, we're asked to complete the following table. So we're given the formula and we're asked to draw the Lewis structure and approximate the bond angles and designate the molecular geometry. So for example, for CH3CN, so first things first, we count electrons. So we have 2 times 4 for our carbons, which is 8. We have 1 times 3 for our hydrogens, which is 3. And we have 5 for our nitrogen. Adding them all up, we have 16 electrons to work with. We put both of our carbons in the center and we surround them with our remaining atoms. We then form 1 bond each. So we formed 5 bonds. So we used up 10 electrons. We have 6 electrons remaining. Now, where do we place our valence electrons first? Where do we place our valence electrons first? Which atom is most electronegative? And don't be shy to type in the chat. I see nitrogen. Yep, so let's complete nitrogen's octet. So we used up 6 electrons. Now, does carbon have a complete octet? Does carbon have a complete octet? Does this carbon right here have a complete octet? Does it have 8 No, it doesn't. Exactly. So we're going to take one of our lone pairs and we're going to form a double or triple bond. Let's ask the question again. Does this carbon have a complete octet? And again, the answer is no. So we take another lone pair and we form another bond, in this case a triple bond. Now the octet rule is fulfilled. And now we look at each of our atoms and we assign the geometry. So this carbon atom has 4 bonds. So, or four bonding atoms, which we'll abbreviate as 4 bonds. Well, let's just write this as 4 bonding atoms. Ergo, our molecular geometry for carbon number 1 will be tetrahedral. Looking at this middle carbon, it has 2 atoms. Ergo, it adopts a linear geometry. So this bond angle for a linear geometry is about 180 degrees, while for a tetrahedral geometry, it's about 109.5 degrees. These were in the note sets that we covered last week. So in terms of our 3D drawing, we're going to make sure to draw our linear center straight as a dart And our tetrahedral center has three-dimensional shape with each of our hydrogens separated by a 109.5 degree bond angle. Now, my question to all of you, is this molecule polar? So if we dissect polar bonds, we see there's a clear polar carbon-nitrogen bond, and it's pointing in a given direction. So there is a polar bond, and the molecule itself, when you add the polar bonds together, has a net dipole. So yes, it is a polar molecule. Does this logic make sense to everyone?
What does polar mean again?
Polar means the molecule, when you add up all of the bond dipoles, there is a net dipole. There is a net uneven distribution of electron density in your molecule. So essentially, if you have polar bonds that are not symmetrically arranged, then you will have a polar molecule. Does that make sense?
And if it's nonpolar?
If it's nonpolar, then it has either symmetrically arranged polar bonds, or it has bonds with no significant dipole, such as like a carbon-hydrogen bond, for example. Does that make sense?
Yeah.
Perfect. Okay, let's look at this next example. So looking at phosphate, phosphorus, we have 5 electrons. Oxygen, we have 6 times 4. And then we add 3 for our -3 charge. So we have 32 electrons to work with. So we have 32 electrons to work with. So we put phosphorus in the center and we surround it with our 4 oxygens. We then form 1 bond each. That gives us 24 electrons. And then what atoms currently have an incomplete octet? What atoms currently have an incomplete octet? Oxygen. So let's add lone pairs to each of our oxygen atoms. Now, my question to all of you is this structure correct? Is this structure as perfect as we can make it? Considering that you've learned about expanded octets, is this structure as good as we can get? Is there anything wrong with this structure? Well, if we look at our formal charges, oxygen's formal charge are each -1, and the phosphorus is +1. So to mitigate formal charges, we're going to kick one of our lone pairs down, and we're going to form a double bond. So now this phosphorus has 4 bonding atoms. So this phosphorus has a tetrahedral molecular geometry and 109.5 degree bond angles. The structure fulfills the octet rule, minimizes formal charges, everything's good. So in 3-dimensional space, your structure would look something like this.
Do we have to know the 3-dimensional space?
Your 3D drawing just has to respect the fact that the bond angles are 109.5. The way that I drew it is slightly more detailed, but I just want you to make sure you're not drawing it flat or anything like that. Does that make sense?
We have to draw the structure in
But as essentially, I just don't want you to draw it like this, you know. I want to make sure that your drawing adequately represents the bond angles. Does that make sense?
Okay, so we draw it just like the way you did on the right.
Yes, exactly. And we did a bunch of examples of how to draw the different molecular geometries in the previous note set. I'm not going to be super picky about them. I'm just making sure you recognize that these molecules have 3D shape and that you're placing your bonds deliberately. Like if you show me something like this, then it's not respecting the 3D shape of the molecule. You're drawing it flat or just with bond angles that aren't matching the actual bond angles. Does that make sense?
Yeah. Oh, and also for the bonding of like phosphorus to oxygen, like so th- so the so the line, so the double lines, is that to satisfy the octet rule for phosphorus?
So
Because
the
phosphorus
double
has,
line is to minimize formal charges. So the octet rule is the baseline rule, but when you look at elements that are in the third row and below, they can accommodate expanded octets. And then to minimize formal charges, since we had a positive formal charge on phosphorus and a negative formal charge on oxygen, we kicked our lone pair down and formed a double bond. This relieved and mitigated our formal charges and resulted in a structure that's more correct. In general, you can form multiple bonds that exceed the octet rule for n equals 3 and below elements on the periodic table, as those elements are large enough and they have access to d orbitals that can participate in expanded octet bonding. Does that make sense?
yeah.
Perfect. So is this molecule polar? Is this atom symmetrically arranged? Is phosphorus bonded to all of our atoms, and are they arranged symmetrically? Do we see any lone pairs on our phosphorus? No, so this molecule isn't polar. It's perfectly symmetrical. So we have polar bonds, we have bond dipoles, but if you add up all of your bond dipoles, they cancel out. And you can prove this with vector addition and geometry, if you're inclined.
Wait, so if there's no lone pairs, then it's nonpolar?
If there are no lone pairs and all of the atoms bonded to the central atom are identical, then yes, in the majority of cases, it will be nonpolar. Does that make sense?
Then it would be polar
If there are different atoms bonded to your central atom, which possess a difference in electronegativity, or if the molecule has polar bonds and the central atom or central atoms have lone pairs. Though that's a shortcut that we discussed. Does that make sense?
yeah.
Perfect. So let's look at this next example, formaldehyde. So counting our electrons, we have 6 plus 4 plus 2, which in turn gives us 12 electrons. We put carbon in the center. We surround it with 2 hydrogens and an oxygen, and we form 1 bond each. We have 6 electrons remaining. Where do our 6 electrons go? Where do our 6 electrons go? What is our most electronegative outer atom? It's oxygen. So we place our 6 electrons on oxygen. Now, does this structure fulfill the octet rule? Does this structure fulfill the octet rule? No. Okay, so we kick our lone pair down. So we have 3 atoms bonded to our central atom. So our molecular geometry is trigonal planar with an approximate bond angle of 120 degrees. So we draw this molecule just flat. Oh, whoops, sorry. Old habit from organic. Let me draw the carbon atoms properly. Okay, is this molecule polar? Is this molecule polar? So if we look at our polar bonds, does this molecule have a net dipole? Does this molecule have a net dipole? Is this molecule polar? Don't be shy to propose a response in chat. Yep, it is polar. Yep, it has different atoms bonded to our central atom, and Your polar atoms and polar bonds are not arranged symmetrically. Yep, so this is polar for sure. Any questions on these examples? If not, let's keep going then. So next we're looking at mass percent, mole percent, and empirical formula. So we're asked to figure out what mass of copper 3 sulfide contains the same mass of copper as 24.5 grams of copper nitride. So we're going to start with 24.5 grams of copper nitride. So we have Cu2 plus, N3 minus. We cross our charges. That gives us Cu3, N2. Let's calculate the molar mass really quickly. So copper 2 nitride has a molar mass of 1 moment, punching into my calculator right now. 218.6. Okay, so in 1 mole of copper 2 nitride, we have 218.6 grams. We know that there are 3 moles of copper per 1 mole of copper 3 nitride. In effect, we're going from the grams of copper 2 nitride to the grams of copper 3 sulfide, which is Cu2S3. So my question to all of you is, how many moles of copper do we have per mole of copper 3 sulfide? How many moles of copper do we have? 2. Exactly right. And then all we have to do is figure out the grams of copper 3 sulfide in 1 mole. Oops, let's check. This should be reversed. We're using our moles of copper as our relationship, and we know that we have 1 mole of copper 3 sulfide for every 2 moles of copper. So now our moles of copper cancel. Now when we plug in our grams of copper 3 sulfide, one moment, just punching that into my calculator. Let's look up the molar masses from the periodic table and just make sure that we get this calculation done correctly. Okay, so we have 32 times 3 plus 63.5 times 2, which is 223. Okay, and now we punch this 1-line conversion into our calculator. And in effect, we've gone from the grams of copper nitride to the grams of copper sulfide. And that in turn gives us 37.5 grams of copper 3 sulfide. Any questions on this example? This is exactly identical or almost exactly identical to a question on exam 2. Any additional questions? Any questions? Okay, let's do another example. Let's continue on with this practice final review. So this next problem is a empirical formula problem. Serotonin is 68.2% carbon, 6.8% hydrogen, 15.9% nitrogen, and 9.1% oxygen. So I'm going to arbitrarily designate hydrogen as N1, carbon is N2. Let's just make things easy. Carbon's N1, hydrogen's N2, nitrogen's N3, oxygen's N4. So fundamentally, the empirical formula is a mole to mole ratio. So N2 over N1 is equal to the mass percentage of hydrogen over the molar mass of hydrogen times the molar mass of carbon over the mass percentage of carbon, which in turn simplifies to 6.8% over 1 times 12 over 68.2. So if we punch that into our calculator, N2 over N1, which is the moles of carbon per mole of hydrogen, we end up with 1.196 moles of carbon per mole of hydrogen. Okay, let's repeat the same process for nitrogen. So N3 over N1. Again, plugging in similar numbers, we have 6.8 over 1 times the molar mass of nitrogen, which is 14, over the mass percentage of nitrogen, which is 15.9%. And that in turn gives us, this equation is in chapter 3 and chapter 4 notes when we discussed the empirical formula. This gives us 5.987 moles of nitrogen per mole of carbon. Finally, let's repeat this calculation for oxygen. N4 over N1, so we have 6.8. Oh, one moment, sorry. Our N3 is nitrogen and N1 is carbon. I have a tendency to want to divide by the moles of hydrogen, so let's redo this calculation really quickly. So this is the moles of nitrogen per mole of carbon. So plugging in, we'll take the mass percentage of nitrogen, which is 15.9%, over the molar mass of nitrogen, times the molar mass of carbon over the mass percentage of carbon. And that in turn gives us 0.199 moles of nitrogen per mole of carbon. And N2 over N1 should be the moles of hydrogen per mole of carbon. Okay, let's do N4 over N1, which is the moles of oxygen per mole of carbon. So we plug in the mass percentage of oxygen over the molar mass of oxygen times the molar mass of carbon over the mass percentage of carbon. And that in turn gives us 0.1 moles of oxygen per mole of carbon. Okay, so this looks like a little bit of a mess, but we can resolve this. This is a little bit of a mess, but we can resolve this if we're very careful with our choice of moles of carbon. So we're going to multiply each of our ratios by the moles of carbon to give us a whole number. So if we have 1.200 moles of hydrogen per mole of carbon, we have 0.200 moles of nitrogen per mole of carbon, and we have 0.1 moles of oxygen per mole of carbon. What common number should we multiply each of these ratios by to give us a whole number? What should we multiply by? How many moles of carbon should we multiply by? What would give us a whole number really quickly? What should we multiply each of these ratios by to give us a whole number? And don't be shy to send a response in the chat. 10, yep, exactly. So if we multiply by 10 moles of carbon, we get 10 moles of carbon, 12 moles of hydrogen, 2 moles of nitrogen, and 1 mole of oxygen, which in turn gives us the formula C10H12N2O. And this is our empirical formula. Does this make sense to everyone? Does this equation and this process look familiar to everyone? Essentially, we calculate the moles of each species, and then we take the mole-to-mole ratio, and then we multiply the mole-to-mole ratio, all of the mole-to-mole ratios, by a whole number to give us whole number ratios that we can write as the subscripts in our empirical formula. Does this make sense to everyone? Is everyone comfortable with this idea of calculating the empirical formula? Okay, let's keep going. So next we're asked to name the following compounds and provide a formula. Oh, these are some extra problems. So let's finish off with some nomenclature. We're asked to name our compounds and then provide a formula. So starting off, this compound is an ionic compound. So we name our cation and our anion. So this is sodium hydrogen carbonate. Looking at the following formula, P2S5. This is a covalent compound, so we name it with prefixes. We have 2 phosphoruses, so we name it as diphosphorus. Pentasulfide. Cobalt, so this compound has a transition metal. So as a result, we have to specify the transition metal charge. So we name this as cobalt 2 phosphide. Remembering that this 2 represents the metal charge, that we're dealing with cobalt 2+. This is a textbook ionic compound. So this is magnesium chloride. Another textbook ionic compound, this time containing polyatomic ions. What do we call NH4? What do we call NH4? Ammonium. Yep. So this would be called ammonium phosphate. Okay, let's keep going now. We're next asked to write the formula. So hydrochloric acid, so H plus HCl. So chloric is derived, hydrochloric, this is describing the hydro prefix tells us we're dealing with a binary acid. Chloric tells us we're dealing with chlorine. So this is HCl, aqueous. Aluminum bromide, so we have aluminum 3 plus, Br minus, we cross our charges, that gives us AlBr3. Magnesium sulfate, so we have magnesium 2 plus, SO4 2 minus, we cross our charges, and that gives us magnesium sulfate, MgSO4. Zinc perchlorate, zinc perchlorate. What is zinc's charge? As a transition metal, what is zinc's preferred charge? 2 plus, yep. Perchlorate is ClO4 minus. We cross our charges, and that gives us ZnClO4 2. Perfect. There are some other questions tacked on at the end of this exam, but this is where your actual exam would stop. And I've written practice exam very similar to your actual exam that you'll be taking. So that's the end of our practice exam review.